We are told that sharks arrive at Rendezvous Bay at a rate of 10 per hour, and that any shark that arrives is either white, blue, hammerhead, or mako, 4 different types of sharks, with probabilities 0.4, 0.3, 0.2, or 0.1 respectively. Then we are asked, well, what is the joint distribution of the number of types of sharks that have arrived after 3 hours? And secondly, what is the expected number of the various types of sharks after this 3-hour period? So this is a generalized task stream problem. And so we have selection vectors, which will assign a type to each shark that arrives. And so chi1 would tell us which of white, blue, hammerhead, or mako shark arrives. And so chi-I in general would handle the I shark. And so it has 4 indicator or Bernoulli random variables, 1 WI, 1 BI, 1 HI, and 1 MI. And only one of those is 1. The rest is 0. So the sum of 1 WI plus 1 BI plus 1 HI plus MI is exactly 1. And these are called selection vectors. So each component is a Bernoulli, but they're more than that. They're selections because they have this added constraints of summing to 1. And the probability then that any selection vector chi-I is equal to 1, 0, 0, 0, meaning that the ith shark that arrived is white, is 0.4. The probability chi-I is 0, 1, 0, 0, i.e. the probability that the ith shark arrived is blue is 0.3. The probability that chi-I is 0010 is 0.2. The probability that chi-I is 0001 is 0.1. Therefore, if we sum these selection vectors up to the number of sharks that arrived, nt, we get a vector consisting of 4 different sums. This is using the fact that a sum of vectors is a vector of sums. The first component of the vector of sums is the counting process, counting the number of white sharks that as they arrive in time. The second component is a counting process, counting the number of blue sharks that arrive over time. And then the hammerhead and the mako sharks in the last 2 components. By task stream developments, we know that these are all Poisson processes, and their rates can be found by multiplying the rate for the shark arrival by the probability of each one. So, for example, MW of t here is a Poisson process with counting rate 10 times 0.4 or 4. And that would count the number of white sharks as they arrive in time. Next, MB would be a 3 Poisson process, counting the blue, and MH would be a 0.2 times 10, which is 2 Poisson process, and the MM for the mako sharks would be a 0.1 times 10, or 1 Poisson process. Moreover, by task stream developments, these are independent. Therefore, MW3, MB3, MH3, and MM3 are independent Poisson random variables with parameter 4 times 3, that's the rate 4 times time 3 for the number of white sharks up to time 3. The next one would have parameter 9, which is 3 times 3 for the blue sharks, and then the hammerhead would be 3 times 2 because the rate is 2, and then 3 times 1 for the mako. And these would be independent. And so we could just write down the joint distribution. The probability that MW3 equals I, MB3 equals J, MH3 equals K, and MM3 equals L. Well, by independence, that's just the probability that MW3 is equal to I times the probability that MB3 is equal to J. times the probability that MH3 is equal to K times the probability that MM3 is equal to L. And so we can just write out those four different Poisson PDFs and multiply them together. And we have e to the minus 12 plus 9 plus 6 plus 3 times 12 to the I over I factorial times 9 to the j over j factorial times 6 to the k over k factorial times 3 to the L over L factorial. And with that just simplifies by adding up the exponents in the exponential to e to the minus 30 times 12 to the I over I factorial, 9 to the j over j factorial, 6 to the k over k factorial, 3 to the L over L factorial. And that's the joint distribution for the sharks after time 3, or 3 hours. The expected number of sharks after 3 hours then is just the corresponding Poisson parameters for these random variables MW3, MB3, MH3, and MM3, because the mean of a Poisson is its parameter, and the expectation of this vector is the vector of expectations. And so E of this vector is E of MW3 in the first component, which is its parameter, which is 12. And the second component would be E MB3, which is 9, and then EMH3, which is 6, and EMM3, which is its parameter, which is 3.